Hey, how's it going? Um, it's Nick here. So I wanted to make a video for my 270 class to talk about some of the details of getting your assembly language program right, getting it to work, telling if it works, and figuring out what to do if it doesn't. Um, and this is something, we're starting to get into larger programs, more complex algorithms, more advanced concepts like interrupts and so on. And a fundamental challenge in any kind of programming is, you write your code and it's supposed to do this, but it's doing something else instead. And how do you figure out why that is and what to do about it, right? And so this is a general notion of debugging, right? A bug is a thing in your code that's causing it to do something incorrect, right? Something different from what you want. Debugging is the process of finding what those things are and then dealing with them. Now, when we build circuits, in 120 or in 250, we have a proto board, right? Well, we're Tinkercad if we're online, but you have a proto board or a breadboard. You put wires in there, you put chips in there, you hook it up to your power supply, and it's supposed to do something. You flip the switches. If it works, that's great. But there's a good chance that the first time you do this, it doesn't work the way it's supposed to. What do you do? Well, some people, rip all the wires out and start over. And that takes a lot of time, and you're not any more likely to get your circuit to work the second time than you were the first time if there's a problem with your design. So when we build circuits, we have a wiring diagram, and the wiring diagram is the blueprint for what the circuit should look like, right? You have a wiring diagram, and then you use that to put the wires into the proto board. And then if your circuit doesn't work, you can use that wiring diagram to figure out the problem. You get a multimeter, you look at the output. If it's got the wrong value, you look at your diagram, see where that value comes from, and then you look at the actual physical circuit and see, if the inputs to a gate are what you expected, and so on and so forth. And you can use the combination of a multimeter to look at values inside your circuit and the wiring diagram to figure out where your physical circuit differs from the wiring diagram. All right, so when we write code, we're going to start with something called a flowchart. And a flowchart is like a wiring diagram for software. It's a high-level view of what our program should do. It's not the same thing as the assembly language code. The assembly language code is like increment this, test that, branch here, that kind of thing. That's super low level, right? That's just about at the level that the hardware can understand, which means it's far from the level we can understand. So the flowchart is closer to our level of understanding. And it's not looking at, move this bit value into here and check that bit. It's a level above that. It's a very sort of broad brushstroke view of what we want our program to do. So I'm going to pick on an example from ECS 120, which is an airplane landing circuit. So we build a circuit in a lab in 120 where you basically have three airplanes with different priorities, and they can request permission to land at an airport. So here's the basic setup. We have three planes. We're going to call them A, B, and C. And plane A has the highest priority. Plane B is in the middle, and plane C is the lowest priority. And at any given point, any or all of these planes can be asking for permission to land, and we're going to give permission to exactly one plane. So if we were to think of this as a system diagram, we would have three inputs. And I'm going to call my inputs A, B, C, and say these are, let me call it request A, request B, and request C. And these can be ones or zeros. 1 equals asking to land, and 0 equals not asking to land. And we're going to have three outputs. These are the permission fields. So this output says we're giving permission to plane A to land, we're giving permission to B, and we're giving permission to C. 1 means permission is given, 0 means no permission. And these are arbitrary. I could just as well say, you know, when you have a 0, that means you have permission. When you have a 1, it means you don't have permission. And then maybe these would be, you know, denied A, denied B. It's totally arbitrary, but you got to know what these 1s and 0s mean. All right, so we still do system diagrams, even though we're doing, you know, assembly language stuff. All right, now if you're given a lab, you're probably told, you know, how you're going to send these values into your circuit and how you're going to get these values out. So I'm just going to make some kind of arbitrary decision here. Now there's no reason why I'm doing this other than, you know, we've got to make a choice somewhere. So I'm going to say that, you know, this is coming from pin RB0, this is coming from RB1, this is coming from RB2. So these are called the pinouts, right? Basically a breakdown of which pins mean what. And so for the permission side, I'm going to go on the other end of port B and I'm going to say this is RB5, this is RB6, and this is RB7. So when we run our code in the simulator, right, we're going to want to put stimulators on these 3 pins. We're going to want to look at these output bits and see if, as our code runs, you know, when there's a request from plane A gets permission, B and C don't. If there's no request from A or B, but C is asking for permission, then there's a 1 for permission C and no permission for those, and so on. So so let's go ahead and flowchart this. And the flowchart lets you sort of figure out the logic without getting too bogged down in the implementation details, like, you know, do I need to use the W register here? Do I need to do a conditional branch? That kind of stuff. It's a level above that. So what might our flowchart look like? Well, you know, put this up here for start. And we know that when we do things with pins, we need to do some sort of initialization. And I could put in here, you know, 7F goes into ADCON, this goes into TRISB, and so on. That doesn't really help me with understanding the flow of my program, right? And a lot of the flowchart is about figuring out the branches and the conditionals. So I could fill this box up with a lot of technical information. It's really just going to kind of confuse this picture. Now, when I turn this into assembly language, I need to know, what do I mean by initialization? So set up the tri-state registers and so on and so forth. I'm just going to say initialization. And then what do we want to know? Well, you know, our biggest concern is A requesting permission, because A has the highest priority. So I'm going to put a question mark here, request A equals 1, and I'll put that inside a decision block. And if A is requesting permission, what do we want? We want to give permission to A. So I'm going to say if this is true, then what do we do? Permission A. Let me write it like this. I'm going to store a 1 into permission A, and 0 into permission B, and 0 into permission C. It's a little hard to read, I know. So if A is requesting to land, I'll give A permission. I'll take away whatever permission B and C might have had, and that's pretty much it. I'm done, right? So what do we do at that point? Well, since we want the system to continually monitor these requests for landing, I'm just going to take this and I'm going to go right back up here to the top. On the other hand, if A is not requesting permission, I'll ask another question. Is B requesting permission? And if it is, then we'll do something similar. We'll put 0 into permission A. We'll put 1 into permission B. We'll put 0 into permission C, and we'll go back up to the top. And you can guess what the last block's going to be. So is there a request for C to land? And if yes, I'll write this a little smaller so I don't have to go to a second page. 0 into permission A, 0 into permission B, and a 1 into permission C. And if C is not requesting, then I'm going to, oh, and this is going to go back up here. If C is not requesting, then I didn't plan this very well. I would go to a new page normally. 0 into permission A, B, and C. So we'll set all of the permissions to be 0, and then we'll go back up to the top. All right, there's a flow chart. And we can tell a lot from looking at this flow chart. We can tell that there is a loop going on. We can tell that whatever the state of the request bits, we're always going to go back up here and check again. And if I didn't put something down here, for example, and I work through this flow chart, and if nobody's requesting, I fall off the end of the earth here, right? That says, oh, there's a problem with my flow. So I can look at this and you know, it looks like it's going to do something repeatedly. It's not going to go into some, you know, unknown state. And you know, you can write this in a way that makes sense to you. So this equal sign business, if I say perm A equals 1, sometimes that's confusing. Sometimes we write that and we really mean, you know, is perm A equal to 1? So, you know, we use double equal signs in C and Java and Python and such to say compare, right? But I'm just going to be totally unambiguous and use an arrow to say I want to store a 1 into here, I want to store a 0 into there, and so on. I'm trying to make this, you know, as clear to me as possible, and then we'll figure out how to make it clear to a computer. All right, so that's what I believe is a reasonable flowchart for this. We'll see if it actually works or not. So where do we go from here? Let's write some code in mplab. So first thing you want to do, make sure you don't have any projects open right now, right? I've got some project here called A1 that's open, and I don't see any source code, so that seems fine, but I do have a project open. So always when you start a new project, close all of your existing projects first. So come here, say close all projects. This window should be open, should be totally closed, and it says no project open, right? You're good to go. Okay, so let's start a new project. So I'm going to say file, new project. And, you know, mostly take defaults. Processor, we're going to do pick 18F1220. And we're going to do simulator. And we're going to do MPASM. And then project name, let's do this. I'm just going to call it planes. All right, so I've got a project. I'm going to right-click on source files. And I'm going to say new assembler file.asm, and I'm just going to call this main. I use the word main a lot for my programs, but that's okay because this is a new project, right? It's not going to confuse this main with the main from lab 2, right? So I'll call it main, and it creates, you know, a window that I can type into. All right, you can play around with these tabs quite a bit. Right now, my source program and my variables window are tabbed together, right? Maybe I want my variables to come down here, so I can grab that and bring it down like this, and now I've got variables, output, and stimulus. I'm actually going to want to fire the stimulus while we're testing our program and looking at variables. So I'm going to left-click on this variables tab, and I'm going to drag it up till I'm highlighting this rectangle. That's going to put it in a totally separate window. So now I'm going to have a stimulus window, and I'm going to have a variables window, and then I'm going to have my source code window. So you can customize this how you like. All right. So let's just write some code. So I'm going to include p18f1220.inc. I'm going to do origin 0. And what do we want? Well, we want some initialization. So we're reading from port B. So I know that I want these to be inputs. So I'm going to set my tris_b to be a bunch of 1s. So let's see. Well, horrible colors. Okay, so I'm going to put a bunch of 1s into the W register and then move WF into tris_b. So I'm going to basically make that whole port an input port. So that's my initialization. And then I want to see if request A is equal to 1. Okay, so, and I know I'm going to keep looping back up here, so I'm going to put a label here. And I'm actually going to put this label in my flowchart just to help me tie it into the code. I'm going to creatively call this label top. So let me go ahead and call this top, and I'll put another comment here. That's the beginning of the main loop. And what do I want to do? Well, I want to see if request A is 1. Well, request A is bit 0 of port B. So remember, port B looks like this. Alright, this is request A. This is request B, and this is request C. So we talked about bit masks, right? I can't just see if port B is equal to 1 or 0, because there might be bits over here. And if all 3 planes were requesting permission, port B would be 1, 1, 1. Well, it's not equal to 1, it's equal to 7. So I can't just say, you know, if port B is equal to 1, then A is requesting permission. What I need to say is if this bit of port A is a 1, then plane A is requesting permission. So we're back into dealing with bit masks. All right. So how do we do a bit mask? We need to put a bit mask into W. So let's do something like move LW. This is a bit mask to check bit RB0. And then let's do the following. Let's say, let's move port B into temp. And then let's end our bit mask with temp. Which will clear all the bits except RB0. And then what's our flowchart say? It says if that bit is a 1, we should go ahead and we should do this stuff. And so I'm going to call this something separate. I'm going to call this, you know, give A permission. And so if ANDing with this bit mask, which pulls off that least significant bit, if that ends up being equal to 1, in other words, not 0, then I want to go ahead and give A permission. So I'm going to say branch if not 0. So plane A has permission to land. And I'm going to put a comment here which says A is not requesting permission. Is B. And I'm going to do the same thing. So I'm going to copy and paste some code. but I'm going to use a different bit mask. So this is to check RB1. Going to put port B in temp. I'm going to clear all bits except RB1. And if it's not 0, I'm going to branch to give B permission. Alright, so I'm going to do one more copy of this. I'm going to say B is not requesting permission is C. So I'm going to use a different bit mask. Pull off bit RB2, and if that's the case, and you gotta be a little careful with this copy and paste business because you can end up with comments that don't make sense. But I don't want to make you sit through a lot of typing. So if C's requesting permission, we'll go to give C permission. Otherwise, no one wants permission. So we're going to take away permission from everybody. All right. So how do we give and take away permissions? Well, these bits of port B, RB5, 6, and 7, right? Those are the outputs that are the permission bits. So we want to modulate these 3 bits. All right, so if nobody gets permission, we should just write a 0 into there. So let's do that. Nobody wants permission. So we'll move a bit pattern. And this takes away all permissions, and then we're going to say branch to top. And now we just have to give permission to our planes for different directions. So give permission to plane A. This is give A perm. So same thing, if we want A to have permission, then we want a 1 right here. So what do we want to load into port B? 0, 0, 1, and then a bunch of zeros. So move LW. So we'll put that bit pattern into the W register, move that into port B, and then we're done. So remember, after we've set these permissions, what do? We go up to the top. So that just becomes, branch to top. And then we'll go ahead and we'll shamelessly copy and paste. So let's give permission to A. Here's where we give permission to B. So this is called give B permission. And I got typos. All right, so here, the pattern we want to load is that. Because permission B is this bit right here. So we want 0, 1, and then a bunch of zeros. So we load that bit pattern, we move that into port B, and then we go back up to the top. And I did that in the wrong order, so all right, and then our last one was give permission to plane C. So give C permission. And to give C permission, we want this most significant bit to be a 1 and then 0, 0. So 1 followed by 7 zeros goes into port B. And so we take that bit pattern, we move it into port B, and we branch up to the top. And that's the end. That's our whole program. All right, So this is really just, you know, a rendering of this into code, where, you know, if request A is 1, we do that, B is 1, we do that, C is 1, we do that. If none of these conditions are true, what happens? Right? We checked A, we checked B, we checked C. If C didn't ask for permission, then we know no one wants permission. So we do this stuff, right? That's this block right here. Put a 0 into all 3 permission bits, and then branch up to the top. All right, so that's our attempt at code. Save your code frequently. I'm hitting Control S to save my code. Let's go ahead and build it. And a few things will happen when we try to build. So I'm getting a bunch of error messages. And the first one I'm getting is found label after column move. So I can click on this, and it brings me up to my code. Line 9. There we go, line 9, right? So what does that mean, found label after column 1 move? That doesn't really make sense. Well, if you look at your code, the color coding can help you here, right? You notice that most of my opcodes are orange and move is blue, right? Go back to table 20-1, look at your instruction set. It's not MOVE, it's MOVF, right? Move file register. And when I type MOVF, hey, it turns orange, all right. Remember, we copied and pasted, live by the sword, die by the sword. So we change all of those to be move F. And don't start looking through here to see what else is going on. As soon as you find an error, fix it, reassemble, right? Because sometimes you fix one problem and 10 errors go away. Sometimes you fix one problem and 20 errors appear. So fix what you know is wrong and then just reassemble. All right, so now we're getting different errors. Symbol not previously defined, temp, and that's at line 9. Oh yeah, remember, we're using temporary space to store a copy of port B. So we need to set that up somewhere. So usually I like to put my variables, right, my declarations of file registers, near the top. So you can use a define statement or you can use an EQU. I'm going to use EQU, so I'm just going to say temp, and I'm going to say equals, or is equivalent to 20, and this is arbitrary file register address for my variable called temp. All right, what am I going to do? I'm going to reassemble, because, you know, chances are this and this and this and this and this and this, all those errors are probably going to go away. So let's go ahead and reassemble, and I'm getting fewer errors now. I'm getting errors saying argument out of range, and it says least significant bits used. Well, that's interesting. Let's see what line 11 says. Move F, port B, comma, temp. All right. Well, the error message isn't necessarily helpful here, right? But it's telling you, you know, that something is out of range. What could that possibly mean, out of range? Well, you know, when we code our instructions into assembly language, we come up with usually a 16-bit pattern of ones and zeros, and some part of that is the opcode, and some part is you know, the D and the A bits maybe, and then there's a file register specification usually. And it's saying that something we're doing in that coding is too big, right? So this is a hard one, right? And this is not a runtime issue. This is a compile issue or an assembler issue. And you just kind of have to sort of look at it and think about it and scratch your head and so on and so forth. And eventually what you'll hopefully realize is that, you know, this is not a valid instruction. We cannot say move F one file register into another. We can say move F port B, comma, W to put it into the W register, but the W register is special. We can't just say move F port B into this other file register. But we can say move FF, right? Move file register to file register. That's that special 32-bit instruction. And so these move Fs probably want to be move FFs, or move F port B comma W, and then move WF into temp. So move FF, move FF, move FF. All right, fix those, reassemble. And we are down to one error. And this error says symbol not previously defined, give a perm. Well, up here I'm saying, if that bit's not 0, branch to give a perm. And give a perm, well, I spelled it giver a perm, so let's get rid of that. And let's reassemble. And hey, it builds successfully. Okay, so we fixed all apparent syntax errors. Now we still could have syntax errors in here, but the errors that the assembler, can't do anything with, the typos and illegal instruction opcodes and so on, those are resolved. Okay, which means now we can run our program and see what it does. So how are we going to debug this thing? So look at your flowchart, right? Well, we don't really have anything we can do for initialization, but let's see if this first condition works, right? Let's check that first if block. So what I'm going to do is up here, we've got our initialization. I'm going to put a breakpoint after we're done initializing. I'm just going to go right here at top, and I'm just clicking over here to put a little breakpoint there. And make sure your breakpoint is on a line of executable code. If you put it on something like a label or a comment, those lines don't get executed, and your code won't actually stop. All right, so let's go ahead and run our code. And I get a different issue from most people. For some reason, my setup, when I first start a project, it says breakpoint cannot be resolved to a valid program memory address. And I'm just getting the evil Cylon eye down here. So stop this, okay? This does not seem to be a problem for most students, but on my setup, this is always a problem with a new project. So if you're encountering this, here's what you can try. Go up to your project, right-click on it, say Set Configuration, go over to Customize, and then come over here to MPASM, Global Options, not the MPASM down here. And there's a little box here which says Build in Absolute Mode. Looking at that box right there, make sure you click that. And then say OK. And now if I go ahead and build this, it should assemble successfully. And if I try to simulate it, I should be able to start simulating. All right. And it says, launching, initializing simulator, user program running, and then it got to line 10 and it hit a breakpoint. Okay, this is exactly what we want. So, so it says debugger halted down here. That's good. And now we can start, looking at stuff. So let me make a watch point. So I'm just going to left click in here, type port B, and let me set up some stimulus inputs. So I'm going to set an input for RB0. And I'll set a second input for RB0. And while I'm in here, let me go ahead and set up my other stimuli. All right, so these are stimulators. And, we use the toggle one in the first lab just because we want to be able to change values. But toggling is confusing because unless you know whether something is currently high or low, you don't know what toggling it does. So I'm going to put my stimulators in pairs. And I'm going to have one pair that says to set my pin to low and another that says set it to high. This takes, a few seconds to set up, but now I can fire, this pin right here and set pin 0 low. I can fire this one and set it high. Set pin 1 low and high. Set pin 2 low and high. It's worth having those separate buttons. It will make debugging much nicer. And all I really care about is port B right now, but maybe I'll go ahead and I'll throw in a watch point for temp. So temp is at location 20. So I'll go ahead and do 0x20. And just remember, this is the value of temp. All right, so let's go ahead and put a plane that's requesting, let's have plane A request permission. So remember, requesting permission for A, that's RB0. So let's go ahead and fire that. So I'll click that arrow, and you get a message down here, asynchronous stimulus set high, RB0 fired. So plane A is requesting permission. And let's go ahead and step, one step. And the first thing you should notice is port B is still all zeros, right? Port B value is 0. So even though plane A is requesting permission, the bits of port B are all 0, which means our code does not recognize that plane A is requesting permission. And whatever else we put in this code, whatever bit masks we use, rotates, swaps, whatever, if port B is all zeros, our code is not going to respond to, raising RB0 to be high. Because raising RB0 to be high is not affecting port B. And that's our next problem, right? Why is port B not being affected? Now, sometimes, some of these tools can be a little flaky at times, but I'm just going to go ahead and I'm going to fire like RB2 a bunch of times. I'm going to fire RB1 a bunch of times, and I'm going to step it again. And something interesting just happened, right? If I look at port B, this third bit turned into a 1. Well, what is that third bit? That third bit is request C. So RB2 did seem to work. That's making this bit of port B a 1. But RB1 and 0, request B and A, no action, right? For whatever reason, these two bits are still 0, and that's a problem. So we've got an issue right now before we get into any of our logic, before we get into any of our looping. We've got a problem with how we're dealing with port B. And the debugger will be very little extra help from this point on. We have to figure out why we're not getting these inputs. And sure enough, we're setting, these 3 bits to be 1s. 1 makes it an input, so those bits should be input bits on tris B. And there's no systematic way to see what's going on here. You have to go back to your notes. You have to go back and look at code that does work, and maybe take a walk and have a cup of tea or something, and at some point, hopefully remember this thing called addcon1, and this edict in the beginning that said always set addcon1 to 7F. And that is what's causing these port B bits to misbehave, because RB0 and 1 are related to this addcon register. All right, so after some period of time, you figure that out, and so let's go ahead and set up addcon1. So we'll put 7F into W, and then move WF into addcon1. This makes all of our pins digital. I'll go ahead and save that. I'll build it, and I'll go ahead and start executing. And I come down to my breakpoint. Okay, so this is what we call rapid prototyping. Rapid prototyping is essential. If it had taken me 15 minutes to do what I just did, to put 7F into addcon1, reassemble, and start my debugger again, if that took 15 minutes, I've forgotten what I was trying to do, right? Your goal in working with this stuff and doing these labs and going through this process over and over is for those things to become second nature. Oh yeah, I want a 7F in addcon1. Okay, you just go in here, you type those 2 lines, Control S to save, that to build, that to run, right? And the more efficient you are at those steps, the less that's going to break your concentration on what you're trying to do, which is, figure out why my port B bits are not getting set. All right, so I'm going to go back in here in my stimulus. I'm going to fire RB0. I'm going to set that high. I'm going to step once. Hey, guess what? That bit of port B turned into a 1. Happiness. All right, so now I'm going to say let's AND W sorry, let's move that into temp. So we did our move FF. Let's go ahead and step once more. Guess what? Temp just changed to, you know, be a match for port port B. And then branch if not 0, give a perm. Well, I can come up here and I can see my Z is uppercased. That means the 0 bit is set. So oh well, we haven't done this AND yet, right? So our W register is a 1. We're about to do the AND operation, so let's go ahead and step that. And it's done the AND, and now our Z is lowercase. That means the Z bit is 0, so the 0 bit is not set. So this branch if not 0 should go ahead and branch. We'll go ahead and step one more time. Hey, we jump down to give a permission. All right, what we do at this point is kind of up to you, but you know, I've been spending, you know, the past 10 minutes, 15 minutes working on this conditional, right? I'm going to reset my simulation and see if this and this also work, right? Before I go ahead and worry about the output bits. So I'm going to stop this and rerun it. And this time I'm going to fire RB1. So I'll do RB1 is high. And I'll start stepping through. So I move port B. Okay, there's my port B. It's got, you know, that second bit set. I'm going to put that into temp. Okay, temp matches port B. My W register is still a 1. I can see that up here. I'm going to AND that with port B's saved value. And temp turned into a 0, right? Which makes sense because our bit mask is, you know, turning everything to 0 except this bit for request A, and since request A is 0, it should leave temp equal to 0. And if I look at the Z bit is turned on because this is uppercased. So when I say branch if not 0, that branch should not happen. So I'll go ahead and sure enough it falls through and says A is not requesting permission, is B. Alright, so I'm putting a different bit pattern into W. We'll execute that. You can see up here W is a 2. And then we're going to copy port B into temp again. So temp is, you know, again, copy of port B. And then we're going to AND our bit pattern with temp. So we'll step through that. And temp is non-0, our Z bit is low, so branch if not 0, give B perm. I believe that branch is going to happen. And hey, we're at the place where we say give permission to B. Alright, so now we got an idea how this is working. So let's try something else. Let's give permission to C. So C fired high, and let's just step through. A is not requesting permission is B, B is not requesting permission is C, and it jumps down to give C perm. Alright, one more test. Let's give nobody permission. We'll step through. A is not requesting permission is B, no is C, no, nobody wants permission. Alright, this seems to work great. We can do one more test. Let's go ahead and give multiple planes requests for permission. So let's say that RB0 and RB2 and RB1 are all 1. So every plane's asking for permission. Alright, so port B is, you know, 111. All the planes are asking for permission. So we copy that off into temp. And, you know, temp is a copy of port B, but now we're going to AND it with this bit mask. And what happens, we've ignored RB1 and 2, right? The purpose of the bit mask is let's just look at that least significant bit. So this bit is a 1, that's telling us A is requesting permission. And when we step through the code, it'll say branch if not 0. Come down, hey, give A permission. Great. So at this point, I feel pretty confident these conditionals are all working correctly. And so now all we got to do is we got to turn on the output bits, right? Set these bits to show which plane has permission. All right, well, we're already in the middle of a test, so we're giving A permission. Let's go ahead and try that. So we'll move this bit pattern into W and we'll move that into port B. Let's watch what happens. So W changed to 20 hex, which is the correct value, and then we move that into port B, and guess what though? Port B did not change. These upper 3 bits are all 0. So we can go back up to the top. We can try this again. A is requesting permission, so we're going to take this bit pattern. We're going to move it into port B. Port B is not changing value. So we have a new problem. And it's not a problem with the logic, right? We want A to have permission. We're at the right spot where this code should give A permission. But the mechanics aren't working. For some reason, putting this bit pattern into W and moving that into port B is not setting port B. All right. So what do we do with this? I/O issues are always a bit challenging, but on the PIC processor that we're working with, if your I/O is not working, main things you want to check with: make sure you're using the right pins and the right bits and the right ports. Make sure ADCON is correct. Make sure TRIS is correct. All right. So look at your port designation, and what do we want TRIS B to be? Well, since these are outputs, those should be zeros. Since these are inputs, these should be ones. And we don't really care about these middle bits. Bits we don't care about, we usually just make them ones, because, inputs are less demanding somehow. We could make them ones or zeros, doesn't matter. But we want TRIS B to have these 3 zeros up here in the top, right? And if we go back to our code, remember when we set up TRIS B, we just loaded in a bunch of ones. So let's change this. And let's change our comment. I'm going to say RB7, 6, and 5 are inputs. RB2, 1, 0. Nope, these are the inputs. These are the outputs. And ideally in my code, I would, have some comments that reflected this kind of stuff, right? So pieces of paper are fine, but and if you do this while you're going, it doesn't feel as much as as much of an added chore. So I'll just say, permission A is RB5. Sorry, A is RB0, B is RB1, C is RB2, and then my output, permission A is RB5. Permission B is RB6, and permission C is RB7. And now if I lose my piece of paper, right, I've still got this information in the code. All right, so 3 planes landing, our inputs are on RB0, 1, 2, our outputs are on 5, 6, and 7. Now, if I had written this in the beginning of working on this code, there's a decent chance that when I got down here and I set up my tri-state register, and I said, you know, all pins are input pins, I would have said, wait a minute, what about these, right? So this is part of the mindset of coding, right? You're not just, you know, typing stuff at a calculator or something. You're in a mindset where you're creating something, and the more you sort of have in your mind the whole sort of larger picture of what you're doing, the more likely your code is going to be, you know, internally coherent, and things like this, you know, will be more likely to get written correctly sooner rather than later. So anyway, so we fixed our tri-state register. Let's go ahead and stop and rebuild and run, and go to the stimulus, and we'll just go ahead and we'll fire RB0, and we know that we'll get to give a permission correctly, so we'll step through give a permission. Okay, we put our value into the W register, we move that into port B, and hey, guess what? Port B just changed, and now this bit is a 1. Plane A has permission. Alright, so now it's all fun. Now we can just keep stepping through. And let's go ahead and give a request for plane 2 to land. And we can step through, and nothing changes, right? Temp is changing, but you know, we still have permission given to plane A. But now let's take away plane A's request, and let's step through. And this time it does not branch to give A permission. It falls through and it says, is B requesting permission? And it will branch to give B permission, and that'll load this pattern into W and move that into port B, and hey, there's B getting permission to land. Alright, so we can keep going. Let's go ahead and give C a request. And nothing's changing on port B. Let's go ahead and take away plane B's request. And now we're checking if B wants permission. It doesn't. So we're asking if C wants permission. It jumps to give C permission, loads this pattern into W, moves that into port, and hey, there's our final state. Plane C is given permission to land. A couple more tests. Let's give permission. Let's give a request for both planes A and B as well as C. And let's keep running. And here we go. Plane A has permission. And now if we take away plane A's request, planes B and C are still requesting. So we'll step through, and sure enough, plane B has permission. And at this point, you know, I'm stepping through really quickly because I believe this code is working, and I'm really just verifying. If I go through, you know, line by line, and I come up here and I check W and Z and all that, it takes a really long time, right? Now, if you know that there's a problem right here, that's exactly what you want to do. But at this point, I'm just kind of confirming to myself that my code is working. So I'm going to take away all requests, and I'll step through this one a little more slowly. So we're at the top. We'll see if A wants permission. No. We'll see if B wants permission. No. We'll see if oh, B still wants permission. Alright, so let me take away plane B's request. So we'll fire that. RB1 is fired low. Let's go ahead and step through. So A doesn't want permission, B doesn't want permission, C doesn't want permission, no one wants permission, right? And I mean, my comments are like helpful here, right? When I'm debugging, I'm right here at a line which says no one wants permission. I don't have to go back and look at my you know, notes that I've written somewhere. It's like right here. I'm at a point in my code where everybody's permission should be taken away. Remember, right now plane B has permission. When I step 2 more statements, what happens? All permission bits go to 0. Nobody's got permission to land. So this is working now, right? And we started with, you know, high-level view of inputs and outputs, a system diagram. We use that to figure out, what our port looks like, which we came back to multiple times, and then we made a flow chart, right? The flow chart doesn't deal with, any of this or tris or anything like that. It's high level. Do some initialization. See if A is requesting, see if B is requesting, give permission to B, and so on and so forth. And then the last thing would be, when you're doing your lab write-up, well, you want to document what you did, right? Now, you don't have to document, oh, I forgot to set addcon1 and this kind of thing, right? The things that get you to where your code is working, you can mention that in like, your discussion or lessons learned or something like that. But you're not going to expect somebody else, who's trying to reproduce your work to go through the exact same steps you did, including, making a typo where you said MOVE instead of MOVF, or forgetting to say addcon1, right? That's not part of the procedure that somebody would follow to verify your final result, which is this code implements a prioritized airplane landing control system. So you list the code in your lab report, the disassembly listing, and so on. But then you talk about, how did you test this? Well, we just did this for the last few minutes. We gave A permission, we stepped through, we saw that this bit turned to a 1. And then we took away A's permission, gave B permission, and we stepped through and we saw that this turned to a 1. And then we did the same for C. And then we set A and C together and we saw that plane A had permission. And then we set all 3 requests and we saw that A still had permission. Then we took away A's request and saw that B got permission. Then we took away B's request and saw that C got permission. Then we took away C's request and we saw that it went back to where nobody has permission, right? So that's the test plan, right? Doing those sequence of steps and seeing what the outputs are. And what did you observe? Okay, again, your observations are not, wow, this is really complex, or changing the font is really helpful. Your observations are, when we fired RB0 to be high and we stepped the code, port B changed to a value where this bit right here turned into a 1. And then when we fired RB1 to be high and we stepped through the code, port B's output did not change because A still had permission, which was correct. And then when we fired RB0 to be low and we stepped through the code again, that bit that was a 1 in port B went to a 0, and the bit for plane B turned into a 1, right? Those are your observations that you want to record, and those you can document, a few of those in screenshots. Now, you don't have to do screenshots for every single step of your tests, right? But it's nice to have, some of that in there, just so, people can compare it to what they're doing. So that's pretty much it, right? So, I mean, that's a lot of stuff. And it's a lot of steps, but this is a process that gets quicker the more you do it, and it helps you feel good about your code. It helps you feel like when your code is working, you understand why it works, right? The worst feeling is, I guess this works. I don't know why. I mean, I changed a few things and all of a sudden it started working, so I guess it's good, right? That's not a good feeling. That's a terrible feeling, like when you're in a job interview and you're being asked to write some code on the board or something, or if you're building code that's going to go into a part of something else, you want to understand it and you want to understand that it works, but you also want to understand why it didn't work if it wasn't working before. And so this whole process of going through a simulator, comparing it to something like a flow chart, right, can really help with that. Anyway, if you made it all the way to the end, congratulations, thank you. Wow, I thought this was going to be like a 10-minute video, and I hate to see how long it is. But there it is, it's out there. So cool. All right, thanks.